In episode 22, titled Real-World Distributions, Skew, Heavy Tails, and Power Laws, the goal is to handle messy real-world data without naive assumptions, because DataX scenarios frequently describe data that does not behave like a tidy bell curve. In operational environments, values often cluster near a small range, while a long tail stretches into extreme territory, and those extremes can dominate risk and cost. If you assume normal behavior when the data is skewed or heavy-tailed, you can end up with summaries and models that look reasonable, but fail exactly where the organization gets hurt. The exam rewards you for recognizing tail behavior from scenario clues and for choosing robust summaries, transformations, and cautious evaluation strategies. This is not about memorizing distribution names. It is about building an instinct for when the mean misleads and when rare events are the main story. We will define skew, heavy tails, and power law behavior in plain language, then connect them to practical choices like percentiles, logging, sampling, and alert thresholds. When you can reason about tails calmly, you will make better choices in both exam scenarios and real decision environments. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.me in the Bare Metal Study Guide series. Skew describes a lopsided distribution where most observations sit on one side while a long tail stretches out on the other, often to the right for quantities that cannot go below zero. In right-skewed data, many values are relatively small and a few are much larger, which makes the distribution asymmetric. This is common in time durations, financial amounts, counts of events, and resource usage, where there is a natural floor near zero but no hard ceiling. The exam may hint at skew through phrases like, most cases are small, but a few are extremely large, or by describing that averages feel inflated compared to typical experience. Skew matters because it changes what typical means, and it changes which summary measures and models make sense. If you treat skewed data as if it were symmetric, you will miscommunicate performance and misunderstand risk because the tail drives pain. DataX rewards noticing skew because it signals that you are reading the data behavior rather than forcing a convenient assumption.
Heavy tails go a step further by describing distributions where extreme values occur more often than they would under normal assumptions, meaning the tail is not just long, but also more populated. In heavy-tailed data, extreme observations are not rare anomalies. They are a recurring feature of the process, and they can dramatically influence averages and variance. The exam may describe frequent spikes, repeated extreme incidents, or unpredictable bursts, and those are cues that the distribution is heavy-tailed. Heavy tails matter because they make common statistical shortcuts less reliable, including assumptions about variance stability and the speed at which averages stabilize. They also increase the risk of being misled by small samples because one extreme event can dominate results and produce conclusions that reverse when another extreme event appears. In operational terms, heavy tails mean that risk is concentrated in the extremes, not in the middle, which changes how you set thresholds and how you allocate monitoring attention. DataX rewards recognizing heavy tails because it leads to methods that protect against surprise, rather than methods that assume surprise is rare.
Power laws describe an extreme version of tail dominance, where a small number of very large values can dominate totals and where scale-free behavior appears. In a power law pattern, you often see that the largest observations contribute a disproportionate share of the total volume, cost, or impact, which creates a world where averages hide the real drivers. This shows up in contexts like file sizes, network traffic patterns, popularity distributions, and sometimes security events, where a few large incidents dominate total losses. The exam may not say power law, but it may describe that a few items account for most of the volume, which is a classic power law clue. When a power law is present, the mean becomes a poor description of typical behavior, and the variance can be so influenced by extremes that it becomes unstable. This also affects governance and capacity planning, because planning for the average can leave you unprepared for the frequent extremes that actually consume resources. DataX rewards you for recognizing when the distribution is dominated by the top tail, because it implies you should focus on percentiles, caps, and tail-aware strategies rather than average-only thinking. Log normal patterns are another common real-world behavior, and they show up in things like income, latency, and file sizes, because multiplicative growth processes naturally produce log normal distributions. A log normal variable is one whose logarithm is approximately normal, meaning the raw values are right skewed, while the log transformed values behave more symmetrically. In operational terms, this means that ratios and multiplicative factors are often more meaningful than absolute differences, and that the tail can be long without being as wild as a power law. The exam may describe values that span orders of magnitude, such as latencies that are usually low but occasionally spike by factors of 10 or more, and those are strong log normal cues. Recognizing log normal behavior matters because it suggests that transformations like logarithms can make analysis more stable and can make models behave better. It also suggests that percentiles, such as the 95th percentile latency, often communicate experience better than the mean. DataX rewards recognition of log normal-like behavior because it leads to practical summary and modeling choices that fit what the data is actually doing. When data is skewed or heavy-tailed, robust summaries like median and percentiles often become the safest way to describe typical behavior and operational risk. The median gives you the middle value and is resistant to extreme values, which makes it a stable description of what a typical case looks like. Percentiles let you communicate the tail, such as the 95th percentile or 99th percentile, which tells you where the worst experiences live without being dominated by a few extreme points. The exam may ask what summary is appropriate for skewed distributions, and the best answer often emphasizes median and percentiles rather than mean and standard deviation alone. This is not because the mean is always wrong, but because in skewed contexts, the mean can represent a value that very few cases actually experience. Robust summaries also support service-level decisions, where the worst acceptable experience matters more than the average. DataX rewards this because it reflects real operational reporting, where percentiles often guide performance commitments and risk thresholds. Transformations are a practical tool for handling skew and stabilizing variance, and logging is the most common example because it compresses large values while spreading small values. A log transformation can turn multiplicative differences into additive differences, which often makes relationships more linear and makes variance more consistent across ranges. This can improve model fit, improve interpretability, and reduce the undue influence of extreme values in training. The exam may describe that values span a wide range or that a few huge values dominate, and those cues often point toward considering a log transformation before modeling or before comparing values. Logging also supports visualization and summary because it prevents plots and reports from being dominated by a small number of extremes. The key is to treat transformation as a method to respect data behavior, not as a trick to make metrics look better. DataX rewards learners who select transformations for stability and validity rather than for cosmetic improvement. Mean inflation is one of the most important practical consequences of skew and heavy tails, because rare extremes can dominate averages and create misleading conclusions about typical performance. If one latency spike adds a huge amount to total time, the average latency can jump, even if most users experienced normal performance. If one extremely large transaction occurs, average transaction size can increase even though most transactions remained unchanged. The exam may describe a mismatch between user experience and reported averages, and the correct response often involves recognizing that the mean is being pulled by extreme events. This is why percentiles are often used in service reporting, because they separate typical behavior from tail risk. Mean inflation can also mislead model training, because a model that minimizes squared error can overfocus on extremes and underperform on typical cases, unless you design evaluation carefully. DataX rewards recognizing mean inflation because it shows you understand how tail behavior distorts naive summaries. Sampling strategy matters when rare but important events live in the tail, because random sampling can miss extremes entirely or represent them poorly. If extreme events are rare, a small sample may contain none, creating the illusion that the tail does not exist, or it may contain one, creating unstable conclusions. The exam may describe rare failures, rare fraud, or rare performance spikes, and then ask how to ensure you capture them. And the best answer often involves increasing sample size, using longer time windows, or using stratified or targeted sampling that still respects evaluation integrity. The goal is to ensure that the tail is represented enough to measure and manage risk, not to oversample in a way that creates a misleading evaluation picture. In some contexts, you may need separate analyses for tail events because the processes that generate extremes can differ from the processes that generate typical cases. DataX rewards tail-aware sampling thinking because it reflects real operational risk management, where you cannot manage what you never observe. Heavy tails connect directly to risk modeling and alerting thresholds because alerting policies are often about deciding which extreme values deserve action. If extremes are more common than normal assumptions suggest, thresholds based on normal-like expectations will trigger constantly or will miss significant events. Tail-aware thresholds often rely on percentiles or empirical distributions rather than on mean plus standard deviation rules that assume symmetry and thin tails. The exam may describe anomaly detection, alert fatigue, or missed incidents, and heavy-tailed behavior is often the hidden reason that naive thresholds fail. In such cases, the best answer often involves using robust baselines, percentiles, or adaptive thresholds that reflect real distribution behavior. This also connects to calibration and prevalence shifts, because tail frequency can change over time, altering what counts as extreme. DataX rewards this because it demonstrates you understand that risk is usually concentrated in extremes and that threshold policies must reflect actual data behavior. When you treat tails as the operating environment for alerts, you choose policies that are more stable and more defensible. Tail-heavy data can also tempt overfitting, especially if you build overly complex models to chase rare extremes without enough reliable evidence. Rare extreme events can look like unique patterns, but if you do not have enough examples, a complex model can memorize noise and produce unreliable predictions that fail in new conditions. The exam may describe a model that performs well on training but poorly in production, or a model that claims to predict rare events perfectly, and the correct concern is often overfitting and leakage. A disciplined approach is to start with simpler models, use robust evaluation, and be cautious about claiming strong performance in the tail without sufficient data and validation. This is also where regularization and parsimony become practical, because they reduce the tendency to chase idiosyncratic extremes. DataX rewards avoiding tail overfitting because it reflects mature understanding that rare events demand humility and rigorous validation. When you can say that complexity should not be used to explain a handful of extremes, you are reasoning the way the exam expects. Communicating tail risk clearly is essential because leaders often make decisions based on summaries, and naive summaries can hide exposure. If you report only the average, you may imply stability, while the tail contains frequent disruptive events that drive cost and reputational harm. Tail-aware communication uses percentiles, maximums with context, and narratives about the frequency and impact of extremes, such as, the median is stable, but the 99th percentile is volatile, which signals concentrated risk. The exam may ask how to report results responsibly, and the best answer often involves explaining limitations and highlighting tail behavior, so decisions are grounded in reality. This is also about governance, because stakeholders need to understand what risks the model or system may miss, especially when decisions are automated. DataX rewards tail-aware communication because it treats uncertainty and extremes as first-class parts of the story rather than as inconvenient details. When you can explain tail risk without sensationalism, you build trust and support better policy decisions. A useful anchor is that tails carry risk and medians carry stability, because it captures the operational lesson of skewed and heavy-tailed distributions. The tail is where rare but costly events live, so it carries risk and drives worst-case planning, alert thresholds, and resilience decisions. The median represents typical behavior and is stable under extremes, so it is often the best single summary for what most cases experience. Under exam pressure, this anchor helps you choose summaries and methods that are robust rather than naive, especially when the prompt hints at spikes, skew, or rare large values. It also helps you explain why mean-only reporting is dangerous in heavy-tailed contexts, because mean can be inflated and misleading. When you apply the anchor, you naturally choose percentiles and robust methods, and you communicate both typical experience and tail exposure. DataX rewards this because it reflects the real-world perspective that the worst few cases can dominate operational outcomes. To conclude episode 22, describe one skewed dataset and then choose safe summaries, because that exercise proves you can apply tail-aware thinking in a scenario. Start by naming the data type, such as response times, transaction sizes, or file sizes, and then describe how most values are small, while a long right tail contains occasional extremes. Then, choose the median as the stable center and choose percentiles, such as the 95th or 99th percentile, to describe tail risk in a way that reflects user experience and operational exposure. If the scenario suggests values span orders of magnitude, justify a log transformation as a way to stabilize analysis and reduce variance issues without hiding the tail. Finally, state how you would handle rare extremes in sampling and modeling, emphasizing adequate representation, robust evaluation, and caution against overfitting. If you can narrate that approach clearly, you will handle DataX questions about skew, heavy tails, and real-world distribution behavior with confident, professional judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.